Can you guys hear me?
Yep.
Okay, good. So just to recap, last week we started this paper. It's on a system that Microsoft has just put out, as you can see by the name here for Microsoft, called Vall-E. Vall-E. I don't know how if it's Valley or whatever, but you guys get it. You pronounce it however you want. So what this is this very, very large text-to-speech model. So it turns text into speech. And previously text-to-speech models, you guys have probably heard them. The sound kind of comes out sort of synthetic, right? A little robotic and thing. In this model, with as little as 3 seconds of somebody's, just a 3-second sample of somebody's voice can pick up not only their voice, but the emotion in which they're talking about, and then emit the text as speech with that voice and the emotion. So if somebody's like screaming and yelling, it'll scream and yell the text. If somebody's, speaking very, very slowly, it will speak very, very slowly. So it picks up the cadence almost like it was defined to be used by maybe voice actors and things like that. So, and this is yet again, we kind of had talked about this a little bit earlier, about another one of these really, really big models. And as we've gone through this, you see like here in this line here, I'm highlighting, one of the secrets of all these big models is the amount of data you'd use to train them. And here they're using 60,000 hours of English speech, which, as they say, is many hundreds of times larger than existing systems that are out there. So this seems to be this thing that when you use these large models, what happens is you get what's called in-context learning, which means you can kind of do things that you were never trained on. And, Chat GPT, GPT-3, which is the underlying model, supports this. Other things are too. And I think we're just going to see this in-context learning from these very large and powerful models continue. Although, as we were talking in the intro, you can also do it if you shrink it down, if you're very smart about about what you're doing. So anyway, that's what we're talking about. And we had gone through, talked a little bit, so we don't bore the people that were here last week. I'll just kind of pick up where we were. So just a couple things here. Let me go back here to this slide. And I'm going to actually go back. This is your typical input that you have from a microphone. We're talking. And if you were to convert this, this would be converted to what we call a Mel spectrogram, which is this picture. You can see time along the x-axis, and on the y-axis, we can hear frequencies. And the thing to note is that the human voice, you see all these little hot spots it has here. That's showing that we have we make echoing sounds in our vocal cords, and they span multiple ranges of frequency. It's not just, a single tone here. It's multiple tones being generated simultaneously. And that's part of what makes it tricky. Go ahead.
Yeah, I was going to say it looks like harmonics, really, is what you're talking.
Yeah, I think some of these are harmonics, Roger, but I think some of these here, like in the upper reaches up here, are not harmonics. But yeah, I agree. These are probably harmonics. That vibrato type thing, the echoing in your throat, if you will, that probably produces these sort of things. And it's really hard for a text-to-speech system to kind of do that. But this model seems to have that knock. So.
And these are just like an FFT, is it, of the
yeah, I think it starts with an FFT, fast Fourier transform, for those that didn't remember that from engineering school or didn't go to engineering school. Yeah, I believe those are starting as FFTs, and then they do. It's also false colored, right? You can see that here to give loudness on the spectrum
over a pretty big range.
Yeah, 0 to 70 decibels. Remember, this is a logarithmic scale, so that's really loud. That's really loud, and that's really quiet. So anyway,
yeah, I don't know if this is important, but you mentioned that the coloration is a log scale, but the frequency domain on the y-axis is also a log scale. Okay.
Yes.
And what I seem to recall is that the Mel spectrogram, as opposed to just a naive FFT spectrogram, it's weighted slightly differently, and basically how it's weighted is based on human audio perception.
That's, yeah,
So,
that,
this is how a human would hear loudness of the different frequencies, not how a sound meter would register loudness of the different frequencies.
Interesting. Huh.
yeah, that's a good point. Usually this Hertz spectrum on a lot of the mills I've seen gets kind of compressed as you get to the upper reaches and things like that. And I think that's to Ted's point, because humans, as if it's over like 14 kilohertz or things like that, we really can't hear it, especially if you're older. Little side here, there's a device called the Mosquito that some guy in England made. And it emits this sound, I think in like the 20-ish kilohertz range, or 22 kilohertz. And the purpose of it is to prevent teenagers from hanging out in front of like a shop or something like that. Because as we age, we lose our ability to hear frequencies above like 16 kilohertz and things like that. So it's kind of interesting, just a little sidelight there.
Jerry, they also have ringtones for your phone that only the kids can hear. I found out about that.
Is that good for like if they're using their phone in class or something?
Yeah. Mom and dad don't know about it.
Or the teacher, or something like that, when that inbound text message comes in. All right. All right, we'll just go back to the paper here. Sorry, guys, got a little sidetracked there. I'm easily sidetracked, in case you guys haven't noticed. But anyway, so that's where our system, but what these guys do is they use what's called a codex, which is a encoder decoder type scheme, where they come out with numerical values, and then they can then move it to the language model space. Remember, we were talking, this whole thing we're doing with like ChatGPT and things like that is using these large language models. So these guys came up with, we'll just convert our frequencies into like language spectra, and then we can use large language models. And we know, using transformer technology, that these large language models like ChatGPT can do things like in-place learning and things like that. And then we can leverage this. So this is really a leveraging of technology coming out of a kind of a different space in the large language model set, written text originally. So kind of interesting, an interesting application of it. Anyway, we went through this last week and we talked through some of the things. And let me just kind of move on. And we had talked a bit about this quantization thing. And this is, if you remember those kind of spectra range that we had, this is actually quantizing, which means essentially compressing their values down into a smaller space of the various frequencies that are within the person speaking. Okay, and the reason they do this is because then it gives us numeric values that we can use to train a model. For anybody that's a little new to machine learning works on training numbers. We turn everything. We turn pictures into numbers. We turn sound into numbers. We turn waveforms into numbers. Impact. If you're controlling a device that's running a sledgehammer, you would measure the impact, and you would convert. You just take the values of that. You don't really care kind of physically what it is. So that's how we operate. Go ahead.
I was just saying, you might want to mention that with transformers, more than turning it into numbers, we turn it into tokens.
Yeah, that's a good point. That's a good point. Roger, why don't you go through that a little bit? Maybe you're maybe a little bit more up on that than I am.
Well, just that, let's see, what's the best way to approach it. This transformers, which is started with this attention is all you need paper, was developed originally for language models. And it used essentially specific numbers to represent specific words or word parts. And then it runs it through a neural net to kind of figure out what part of the sequence of tokens that it should pay attention to in next step, and that would iterate multiple times on that. So the transformer started as a language model thing. It's been applied for a lot of different things, but it is based around this idea of a sequence of tokens. So here, we're not converting it in, I don't believe, converting it into real numbers, it is converted into a sequence. The audio signal, which is an analog waveform, is converted into a sequence of tokens, quantized tokens.
Right. It's not words actually. We're converting what are called phonemes, which are the parts of speech of a word that your voice makes. Remember all those little frequency we showed there, but it's converting those little pieces of it, and then it kind of pieces them together because you naturally assemble your phonemes in a certain way, and so then that's kind of how it learns to be like you.
Jerry, maybe I got this wrong, but I thought in this case, we can think of these sequence of tokens as kind of that replaces the analog to digital converter. So it's, the Vall-E works in waveforms, quantized, tokenized waveforms, not in phonemes.
Well, but the thing that comes in is it learns to recognize the pattern of phonemes, maybe is a better way to say it.
What spit out is,
Yeah, does that make sense? Okay.
Yeah, I think so.
Yeah, okay. So anyway, we went through all this stuff last week. So we're going to start kind of right here. And in fact, here is, well, here we go. So this is kind of how Vall-E kind of works inside, as much as the paper on something that is proprietary to Microsoft that they will tell us how it works. This is, we can have a long discussion about proprietaryism some other time. But, so this is that encoding that Roger was kind of alluding to. And what they do is stack these things into one of 8 buckets, these phonemes, which are the parts of sound. So if you say hello, there's huh, oh, it's not quite it's not a syllable. It's just sort of sounds that your mouth would form to create the word. That's the best way I can describe it. If somebody has a better description, let me know. But anyway, what it is creating, it's creating 8 kind of buckets, if you will, of those to put them together, and then it's stacking them up to get the full time. So if this, if we go from 1 to T, this represents maybe T is, I don't know how fast you talk, and it depends how fast you talk. But maybe this can be up to 100 or 200 or 300 of these sounds that you would talk in, let's say, 10 seconds or something like that. Okay, so that is kind of the data that's being fed into our models here. Okay, so let's see here. Yeah, so I won't.
Hey, Jerry.
Yes, sir.
Sorry to interrupt, but I just want to make sure it's clear that 1 to 8 business you're talking about, that was from the architecture diagram you showed. The quantizer has 8 units, and so it spits out 8 numbers.
Yeah, in sound they call it stages, but yeah, it's 8 numbers out of that. Yeah,
right. So the time dimension on that scribble you made to the right is vertical.
Yes, and
the data dimension is horizontal.
Absolutely. Yes.
I just want to, in case.
No. I appreciate that. Yeah, you know how it is when you're trying to go over something. Well, this makes sense to me, but if it does, it may not make sense to others. So I really appreciate Ted.
Yeah, it's much better with your diagram than just trying to read the text. But I just wanted to make sure that since we have the benefit of your diagram, that people knew what the axes were.
Yeah, but then you got to try to read my handwriting, which kind of sucks. So, I blame the Apple Pencil on my iPad for that. But anyway.
I have another question, Jerry. So is the capital T the same as the capital L or L+1?
Let's see here. Oh, in the corresponding phoneme transcription.
I think so.
Yes, I would think it would be.
T, I would guess T, it's supposed to be at a 75 hertz sampling that they did. So T should be time in seconds times 75. L is I would interpret to be the number of phonemes in that audio sample.
Yes, I think you're right.
They may not be the same.
Yeah, and in fact, it probably wouldn't be
Probably wouldn't be. If you could speak 75 phonemes per second, that'd be pretty impressive.
Yeah.
Not even Sharon can do that.
Yeah. Okay.
Okay.
Yeah, we'll just move on from there. We'll leave that one right there. Okay. So So during inference, and for those that are new to machine learning, there's two phases in machine learning. There's a training with data, and where we train, we have these models, neural network models, and all their values are kind of in some sort of quasi random state, for lack of a better term. And what we want to do is train it with data and then tweak all those values in the model so that they do what we want to, be that recognize people in pictures or generate speech or, generate the next word in our chat GPT thing. When they're generating those words, it has to be trained to do that. So that's what the training stage is. Inference, then, when you see the word inference in machine learning, it means, okay, you've got the trained model. Now give me the data and I'm going to do whatever task you trained it on, and I'm going to, output whatever I was trained to output. So if you're new, just keep that in mind. Training is training to get the model ready to go. Inference is when you use the model to produce the output. Okay. Okay, so it says during inference, we use a phoneme sequence and 3-second enrolled recording of the unseen speaker. We'll see this in another example in a little bit. Yeah, and we'll see that in action. Essentially, though, what's so cool about Vall-E is that to train it in your voice, in your cadence that you're doing because you're playing in a Shakespearean actor or something and you want to speak in a Shakespearean actor, and you're really enunciating and things like that. To train it, it only needs a 3-second sample of your voice and not saying the words that you want. The text is in the text. So they can just pick up a recording of you somewhere and have you say words that you never said before. Little problem there, but from a security issue, and we'll get to that at the end of this thing. Okay, the neural decoder, we talked about the codec decoder synthesizes high quality speech. In training, this thing uses those quantizers that we talked about in kind of a hierarchical fashion. The first one, quantizer here, is something they call autoregressive, and we'll talk about that in a minute. But it's sort of picking up kind of gross sounds and things like that, sort of picking apart the things. And the later stages then are sort of fine-tuning that. And let's go down to this picture. This may not make sense if you're not a transformer person, but if you're going to do machine learning, you will become a transformer person. That's straight. Transformers have this magical property of what they call attention. Previous speech models, we try to say, oh, convert this from English to French. And, and when you switch between English and another language, the noun may move, subject verb relationship may change over time. So the model has to be able to figure that out. And also, as you go along, you may say a whole bunch of stuff. We went to the store, blah, 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 blah. And then and now, what is this he we're talking? No, Bob and I went to the store, blah, blah, blah. And then who is he? In previous models, it had forgotten who he was, that he would really be Bob. And then it would, from there on be kind of screwed up. The attention model gave us a way to, quote, attend to various tokens in our language model and keep track of that. And this is why when you run Chat GPT, which runs the GPT-3 model, which uses these transformers underneath, that's why, you can say something like that and you can say it, and it knows that it refers to the thing you talked about 2 sentences ago, just because this long model has been trained using transformers, and transformers can attend to previous tokens. And attend means they just kind of pay attention to them. So in this thing, we have 2 different types of transformers. We have something called an NAR, which is close to probably what being used as a decoder, and is close to what we more classically think as a transformer. And then we have this one called an AR, which is the one that's learning kind of the gross level. And notice this AR only attends to things to the left. And what that means is, if I were to write that out, Bob and I went to the store, had a great time, saw some stuff, and then he bought, how it would figure out where he was, it would have to go, Bob would have to be on the previous, we would have had to have mentioned Bob previously. These NAR tokens, though, can attend to all tokens, so it can take a look ahead, take a look back, and figure out, hey, what is the right thing to do in all that context? And I don't know if I explained that correctly, but that's kind of the difference between the twos. Okay. And then here they say this, that when we come, and here, this is kind of, this mathematical summation here is kind of combining the two models together. And in fact, here you see this NAR, they're distinguishing it here. Oh, I'm sorry, this is just the one for the NAR. And here's the one for the AR, and then they're going to put them together. I'm getting ahead of myself. The other thing we worry about in machine learning is speech, not only the quality, the output, but we worry about how fast we can do it. Because if it takes us a week to get the answer, it's probably not a useful type thing, Okay, so we'll move on here. And this spends a lot of time kind of going through a lot of the autoaggressive codec model. And let's just kind of pop down to here. They say during inference, given an enrolled recording, we should concatenate the phoneme sequence with the enrolled recording and the phoneme sequence for the synthesis together. Yeah, and this is one of their tweaks they're doing to kind of put the pieces together in a way that the enrolled thing, which is that 3-second sample I was talking about, is used to kind of force the sequence of how the speech is generated into something that matches that. So they kind of combine those two. I did a terrible job of explaining that, but that's what it does. Apologies.
Jerry?
Yes, sir.
What do they call that? Enrolled recording. So does that mean that they have kind of a standard audio clip that they?
No. Let's, in fact, that's kind of important. Let's see if we can kind of, let me just go back here. Gosh, I hope this hyperlink works. Yeah, I had to read that like 8 times to get that. You remember we kind of went through this last time. These are samples. Okay, so they're going to have it say these, here's the text that the model's going to say. They moved therefore cautiously, blah, 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 blah. The enrollment is this speaker prompt. This is 3 seconds of the speaker. So let's hear it.
He descended the ladder and found himself soon upon firm rock.
Notice that none of those words were in here, right? Now, when they took this text and push it through a regular text to speech model, they get, well, this one here.
They moved thereafter cautiously about the hut, groping before and about them to find something to show that Warrington had fulfilled his mission.
Okay, very robotic, right? Anybody disagree with that? No. Okay, now using this speaker
He
prompt
descended the ladder and found himself soon upon firm rock.
that had nothing to do with those words. Once they push it through Vall-E, now Vall-E can generate this text in this voice.
They moved thereafter cautiously about the hut, groping before and about them to find something to show that Warrington had fulfilled his mission.
Do you notice it's much more natural? It even puts stops in there because this particular speaker stops at certain times. So that's kind of its cool thing. So that is the difference between those two. Does it make sense?
Yeah, so the enrolled recording then is just the one that is going to capture the style. And so it's just the acoustic side. It doesn't include any phoneme or anything like that. We just know it's 3 seconds worth of sound. Is that
well,
right?
they rip it apart. They rip apart the phonemes and things like that for that. And then, I don't claim to know exactly how they put that together, and I didn't quite see it document in there, but that's what they're doing. And
Okay.
yeah. Okay,
Thanks.
no problem. Thank you for keeping me honest on that. Okay. And here, let's see. Then we have we have the one, blah, blah, blah. Let's see. Yeah, and this kind of goes into detail. I remember we had the AR, this AR transformer and the NAR. AR is short for auto-regressive context, codec language modeling. Generates tokens, and this is only the first quantizer. Remember, this is kind of the one that sort of does the overall sort of thing, and the rest of them sort of fine tune. And the thing is, well, we talked about this here, I guess. The inference, they use the enrolled recording, and we concatenate the two together to produce that sound, if they will. And so they use that person's voice sample, if you will, to kind of tune this model, the autoregressive model, one that attends only to the left, onto the left side here of the transformer. Okay. The not autoregressive, remember there were 8, back here, I'm gonna go to this picture here. We had 8 of these. The autoregressive lives only here in column 1. Okay. So the values from that end up in column 1. And then in column 7 through 8 in the ones for the non-autoregressive transformer, which means that they can then use like words previously spoken and kind of connect them up. Because you know how you say something and you may say, okay, and you say okay like that just if you're speaking it out. But if you've been yelling at you know, or you're having a fight with your spouse or whatever, it's like, really, you slam the door and it comes out completely different. So those sort of are conditioning for that. So this is what they do. And as I said, we employ the non-autoregressive model to generate the 7 other codecs, 7 other quantizers. So we quantize the sound a little bit.
So is each one of those quantizers just like a different bit of that sound? Like, is it just a portion of?
No, the quantizers are just numeric values. They're just, well, yeah, I guess it would be the way you're saying in this. Yeah, this would be like in that spectrum diagram we talked about.
Mm-hmm.
It would be, it would be fine tuning those, if you will, in the spectrum.
So Jerry, you said
Mhm.
earlier they're
Mhm.
they're hierarchical.
Mhm.
So in terms of procedure,
Mhm.
Danya, what happens is the first quantizer has whatever its value is. Okay, call it like a rounded number. For what's in there. It's a vector. It's not a single number, but right. So then what they do is they subtract that out, and they run the second quantizer on what's left, and then they subtract that out and they run the third quantizer on what's left. So like if you think about like gradient boosting machines or whatever, like you're running each successive step on just the residual. Okay. And so it could be the case that a lot of the time you tend to get the higher frequencies more left over in the residuals later on, but it's not technically requiring that the earlier ones don't include the higher frequencies or whatever. It's just the main signal gets picked up and then it's just using the residual and the residual 7 more times, if that helps.
So
Yes.
Ted, should I be thinking of this as like different bits in the A to D, if I'm on the encoder side, in the A to D? Or should I be thinking of this as creating a soundtrack by adding, multiple signals together to where I get something that is rich?
Yeah, I think it would probably make better intuition if you were thinking of it as like, if you're like, oh, wow, the main thing that seems to be going on here is these loud guitars. And once you've subtracted that out, then you're kind of like, there seems to be, quite a bit of whatever coming from,
Yeah.
The guy
this.
hitting
And
a
then,
cymbal or
then,
whatever. Yeah.
the lead singer and then the background singers or whatever. It's not literally that, but I'm
that's
saying
kind of-
that's probably a closer intuition than to say you're breaking it up into bits or different frequency bands or
Right.
whatever.
Okay, great.
Yeah, there's definitely no association with the frequencies on that. And I think Ted, that is a really good example. Appreciate that.
The
And by the way-
example that you
Go
um,
ahead.
the example that
Go
you
ahead.
gave, Ted, of the residual computation, are you describing how vector quantization works, or
No.
also
I'm
struggling
describing
to like understand
Right.
this
I'm describing what the
representation?
goal, what the target of the vector quantizer is. So you run your signal through a bunch of CNNs, and so it may not even be in frequency domain anymore.
Mhm.
And so you've got this encoded data, and then you basically run it through a quantizer, which rounds it to the nearest of, I think it's 1,000 entries in the code book. Okay. And so
Okay.
that would get you a pretty rough, close approximation to the sound, like someone with a deep gravelly voice would clearly, be different from someone like me, and clearly different from someone with a high pitched voice, right?
Mhm.
But it's not going to be perfect because there's only 1,000 options,
Mhm.
for each time step from the code book. So whatever that error is, the difference between the real entry and whatever you looked up in your dictionary, that's what the next codec is going to, the next quantizer is going to say, what's my closest of my 1,000 entries for?
And is it 1,000 for all 8 bits, or is it 1,000? I mean, all 8 places, all 8 numbers, or is it 1,000 for each?
Yeah, if Jerry, if you scroll up to that picture, you can actually see where they have like a minus sign showing they're subtracting out the quantizer, and then each quantizer has a code book of 1,000 dictionary entries.
Where are you seeing this, Ted?
I think it's up like page 3-ish.
Yeah. So it's kind of like an 8-headed
There.
recorder where you can bring in 8 different channels, and each of the
I
vertical
see.
columns is the sequence for each
Oh.
channel.
So you could have like 1,000 to the 8 different combinations.
Correct. Yeah. So it's quite a bit of
That's a
resolution at the
lot
end
of
of the day.
combinations.
Yeah.
Yes.
Yeah.
Yes. But they're all vector quantizers. So
Right,
like,
right.
I mean, if some people don't really know like audio or whatever, like imagine that I had a super high resolution picture, okay, from like a great camera. It's like whatever, 100 megapixels, okay? And then like you turn it into like a 64K JPEG, right?
Mhm.
It's going to lose a lot of the details. But if you subtract that JPEG from the original image and you say, now make a JPEG out of just that, and then you did that 8 times, then when you reconstructed it by adding back together those 8 JPEGs, you would get a lot better of a picture than just one JPEG would ever give you.
Mhm.
Does that make sense?
Yeah, thank you.
And so those JPEGs are not necessarily in a particular color or frequency domain. They're just whatever was left over that the first one missed.
Mhm.
Right. That's some pretty good intuition there, Ted, I think.
All right.
Yeah. I didn't even notice
Yeah,
the
thank
minus
you.
sign. But that makes sense, right? And then we got the residuals dropping out of everybody and then being pushed to the next quantizer. Gosh. Okay. All right. Where were we? Were we here? We were talking about that. Okay. Let's see here. Let's actually, yeah, so this is the non-autoregressive, and that's where they're pushing the other quantizers. And I think this is more mathematical formulation for, I didn't see a lot of, I didn't get a lot out of it, and it's maybe just me here. But, I think that picture that you mentioned, Ted, is actually a better, clearer example. Because here it's talking about stage 1 to stage 1 minus 1, and you can see here they're just kind of summing out the various values and things like that. But how they're doing it, I think, is better shown by that picture that you suggested we look at. All right. So anyway, that's sort of our training loop. Once we got this thing trained to be able to do that, then we can use it in inference here. And that is when we then take that text that we have and that 3-second enrollment that we kind of played originally, and we see what we can, what the model, how we can change the model slightly to fit that particular 3-second enrollments values within the frequency and pattern of how they speech, and frequencies they speech, and whatever you want to call it that makes it a unique voice. Yeah, and interesting, they're saying they can do it without fine tuning because the model's believed to. Oh, okay. Yeah, they say they could do it without fine tuning in a lot of cases, but then they say for language model you can do this, and I think some here they say, however, in context, TTS of existing TTS systems is not strong. So they've brought the in context, I guess, learning capabilities. And this was something where I had a little bit of trouble following their logic here on this, I have to admit. And they just talk about what they do is they first, convert the phoneme sequence, push it through the model.
So Jerry, you ready for another analogy?
Go ahead. I love your analogies, Ted.
I love analogies. They don't always work, but like, okay.
But if you
So
get, yours usually do though. Yeah, go ahead.
ChatGPT, not in the audio domain. Okay. You can say, like, let's just take some well-known story or whatever. Like, I don't know what's a well-known story, but the intro thing to the old Gilligan's Island TV show, okay?
Mhm.
Right? You can say, tell me that back in the style of a 1920s Chicago, mobster. Or tell me that in the style of a 5-year-old who loves princesses. Tell me that in the style of someone who constantly repeats themselves. Okay, whatever, right? You've seen some of those examples of ChatGPT. They're not retraining ChatGPT. It's just because it's in your prompt. It's now going to say the same thing about, I don't even remember what it is, 8 people who went on a 4-hour cruise, but the storm kicked in and blah, blah, blah. But it's going to say it differently, okay? In this case, because it's a text-to-speech thing, instead of literally choosing different words and idioms, it's going to choose the different decodings to change the tonal qualities, even though the phoneme is going to, in all cases, be the exact same thing where you say, fa, o, for 4, or whatever, I don't know, our cruise, it's going to be the exact same phonemes, but the speed, the tone, that's what it gets to vary based on the context it has, but without ever retraining the model. The model weights are completely frozen. This is all just at runtime inference time.
Right. That is a really good analogy. Others? What do you? That? Oh, that was really good, Ted. At least I thought it was. I don't know about anybody else.
You can't have an ML meeting without bringing up ChatGPT. So I've ticked that box.
Yeah, we don't have to do the okay, let's see here. And then that's kind of it. That's how it works here. They do have two things you'll see here, and we'll go through real quickly. The what would you call it? They're experimental things. And this is, your standard stuff for machine learning, that every time you write a paper, you got to prove your work. So with Vall-E, they were looking at generating context for an unseen speaker, and the model's given a text segment of the enrolled speech and the corresponding transcript. And so then when we see values for just for Vall-E, that's what they're talking about. So with the phoneme prompt, as we just talked about, and the acoustic prefix, excuse me, which is that acoustic little enrollment speech thing. Vall-E generates the acoustic tokens for in the voice cloning of the speaker. And over here, we're saying we use the whole transcript, in other words, the whole thing that they've produced. And like if it's it could be, you know, the reading of the Bible or something like that, could be the whole transcript. And then the first 3 seconds of the utterance and the phoneme prospectively, and then ask it to generate, you know, kind of a continuation sort of thing. All right. And
Jerry,
yes, sir.
can I ask for another TED analogy? So I'm not completely clear about why you have an autoregressive on the first stage and non-autoregressive on the other 7 stages. What's the advantage or why?
I can tell you that they
Okay.
talk about right here. Read this area here. What I've highlighted here.
Okay.
It says it provides a good trade-off between speech quality and speed on the one hand. So this is almost like them arguing with themselves if you read this carefully. It says the AR model is a more natural choice with its flexible acoustics length prediction. On the other hand, for consecutive stages, remember output slots. Yeah. And
So let me see.
the big one, I think, is this: the NAR can reduce the time from O to T, you know. And
Okay.
I think the fact is that you can do it faster and still achieve reasonable results.
So let me make sure I understand. Let me read this back then. So the first stage, autoregressive, takes longer to compute, but it's able to kind of predict the cadence and the length of the output.
Yes.
The sequence length of the output. And once you have that as kind of a condition, then you can use the other non-autoregressives to fit at that cadence. And those are quicker to compute. Is that right?
Because you can obviously parallelize it, but you can
Right.
also, yeah, you know, and get to time of big O1, right? So
Gotcha.
right now, so
Okay.
yeah, yeah,
That makes sense.
yeah. I thought it was more of a tuning thing, but I think it's you know, well, it's good enough, and I can get better speed this way.
It's really, yeah, it sounds like it's really a compute time trade-off.
Right. Well, you know, it's typical engineering, right? You make all these different trade-offs. Nothing's perfect.
So
in
it looks like
engineering.
the autoregressive is the only one using the transformer, and the transformer is quadratic with respect to sequence length. And so it looks like the non-autoregressive is just, it may be expensive, it may have a high constant, but it just runs through once. It's not looking at anything that happened prior. So if you're currently saying I'm making the, you know, the PH, the F phoneme for the beginning of the word for, then it's just thinking, how do I make the F sound in this speaker's voice? And it's not worrying about anything else that came before, if I even should be making that sound. It's just saying, how do I properly make it sound like my example person?
Right. If you look here, notice this, they have a EOS, end of sequence token, and it never appears up here in the non-autoregressive model.
So the AR transformer, that decoder would be called once for every token, right? Generate the next token, generate the next token, generate the next token, right? Many times. That there's still a transformer in the NAR block, right? But it's able to look at 1,000 tokens and say, okay, generate all the 1,000, you know, channel 2 tokens.
Yeah, I view it more like, you know, how in language, in regular language models, the NAR is a lot closer in my mind, and I don't know that that's absolutely true, but in terms of its operation, it's a lot closer in that it maintains the memory, and what it's maintaining the memory of is the various sounds and things like that.
But it's still,
I think
a transformer with attention
yeah,
all over the entire sequence.
So what I said earlier is not right. What you said is better, Roger. They're calling the NAR a total of 7 times regardless of sequence length. They're calling the AR as many times as the sequence length.
Yep.
Yeah.
And that's how they change. That's where that other thing said, whatever, T versus 01. Technically it's 07, but in
Right.
computerese, 7 is the same as 1, right? It's just a higher constant,
Yeah.
but that's the thing, is that the AR1, you do have to call as many times as your sequence length. Yeah. So thanks for correcting that.
Makes sense.
Yeah, only takes us 3 or 4 people who understand all these, but that's okay. Yeah. And then they have a continual one. We talked about that. So let's go to the numbers. Let's see what they trained it on. That's always a fun thing to see if you could do it here. They trained it on 16 NVIDIA Tesla V1s. That's, a reasonable amount of hardware, but nothing you couldn't buy online, buy time on pretty reasonably. GPUs, batch size 6K, GPUs 60, 80K steps. That would have been a little pricey probably.
Yeah, do they give a wall clock time? I don't see that.
Hybrid model, untrained, unlivable specific transition, best phone and paths. These are just how you structure the data. I'm not seeing, did we run this for, you're meaning how many CPU days, weeks, or whatever, GPU
Yeah,
days,
exactly,
weeks. And
exactly.
yeah. That I don't remember that, but I won't say I was looking for it. As we go through there, maybe we'll see it. It'll pop out. Okay. So anyway, let's go to kind of the numbers here. Two metrics they're using here, word error rate and speaker similarity, which is something they have a way of measuring. I don't know how that is. Vall-E, which with just a little, the short thing, they were able to achieve 0.58, which is, I guess, much better than that, which is your TTS is a kind of state-of-the-art text-to-speech system now. And then with this Vall-E Continual, when they have more data, what their word error rate drops down. But interesting, their speaker similarity got a little wonkier, probably because remember, this thing is capable of matching, of taking, you saying things in like a funny voice or very strong emphasis and things like that. And my guess is the Continual takes a look at the whole, like if I were to give you a whole page of text, it would take a look at how you said that whole page of text. And that may have some variance in it, I think. I think that's what's going on. I didn't actually find that, but let's see here. But anyway,
Hey, Jerry.
yes,
I
sir.
didn't get a chance to look at this, but I'm noticing that the ground truth has
Mhm.
scores.
Mhm.
And
Oh,
there's
yeah.
like a word error rate.
Mhm.
And then also, because sometimes the 3-second sample sounds a little different, like you said in one of them, right? The woman sounded more like in a phone booth in the 3-second than in the main one. Like
Mhm.
you notice the speaker similarity on the actual same person is only a 0.75.
Yeah, that I hadn't noticed that, but that is an interesting observation.
Like those are kind of crappy scores for like the ground truth.
Yeah, you would expect them to kind of be like almost no errors. But well, here's the thing. They're using 60,000 hours of people speaking things from audiobooks or, reading whatever historic documents or whatever they got it from, wherever the data set came from. And undoubtedly there are going to be some oopses in that much, human people reading that time. So that may be accounting for some of that, but that just seems these numbers seem way too high, because I would assume those would be very, very low, occurrences. So yeah, that is that.
Right.
Yeah.
I might need to go back and see how they calculated these, because maybe the computer model will report a WER that's actually higher than the actual error rate. Like the computer will think the speaker messed up, but in fact, maybe they just have a funny accent or something and they said the correct word.
Yeah,
something.
they actually go into some of that down here. And some of their things, I'll get down to it here. The VCTK one talks a little bit about that. These are Well, they are English speaker, but some of them are British. So, to Americans, that's, that's a little bit different. But they are supposedly all native English speakers. Okay, so it's doing a pretty good job, I think. Much better than anything we currently have, which is kind of the goal they were trying to beat with this. Let's just kind of move on to here. Yeah. Well, in fact, maybe we'll just move right on to this one here so we can move us along. This one is your TTS is once again the basic one, or the current state of the art. Vall-E, did better on it with that. And the ground truth, it's getting pretty close. Now, this VCTKA has people that are not native English speakers. So some of this may be because of that. Okay. And let's see here. They also have, this is another thing. In the VCTKA, they have noisy environments here. So that may be why they get some of the words wrong, or the system recognizes that some of the words, thinks that some of the words are wrong. And here they're showing, time and seconds can be, for two different speakers, can be kind of radically different, if you will, on the various ones. Okay. So they kind of nail it out, and their analysis is that, the older systems have a mapping one-to-one input-output waveform type thing. Since they do it with discrete tokens, and I'll read this to you, as its output is diverse for the same input time due to the randomness of inference. And so essentially they can match the images, the enrollment sounds and things like that, including the acoustic sort of things. And that's, I just got ahead of myself. So this is the acoustic maintenance they talk about. So they say where acoustic prompt has reverb, they could synthesize speech with reverb as well. And that's pretty bizarre that you can say, oh, this guy's, the boy in the bottom of the well or something like that. So it needs to sound like he's in the well. So you, voice actor playing boy, we're going to put you kind of, in a closet or something like that. And it's going to, with no padding on the walls, and it's going to reverb around. And so then when we play this and you're having this long dialogue between you and the rescuers, your voice is always going to have this kind of reverb sound. So you sound like you're down in the well. So I thought that was pretty cool. And then emotional maintenance. I won't pick on William Shatner anymore, but some people really emote when they speak and really throw a lot into it. And if you do that in the sample that you give them, it is preserved into the generated speech when the text is converted. And I wrote, this is hard to do in TTS because I've been looking at TTS to try to make my life easier for a long time. Anyway.
And also, nothing was ever labeled with an emotion in the training.
Yeah, that's true. I mean, yeah.
So not only is it hard to do, but they did it without ever actually telling it. Oh, by the way, this person's angry, this person's whatever.
Yeah, but I don't know whether that would help unless you wanted to find what angry sounds like, ahead of time. I think it's just like, just emulate the sample, and whatever it is type thing. And it's up for the human actor, maybe in that particular case, to define what angry sounds like.
So
that's my take.
Jared, do you have any idea how this could be controlled? In other words, in your application, there may be times that you want to be more, put more emphasis on something, or be a little lighthearted, talk a little light, softer spoken, or whatever. Now we're going to want to embed that into the phoneme sequence, right?
Either the phoneme sequence, actually in the text.
Yeah, in the text somehow.
In the text, I would, I would do it, having some sort of meta character that says like, in a little laughing voice or something like that,
Right.
bracket laughing voice, blah, 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 slash laughing voice, where you stop or something like that. So this is, kind of the core system. I think there you would build that on top of this, to be real
Okay.
honest. Does that make sense?
Yeah, I think it does. I'm guessing it gets some of that already just out of the context, right? Because it knows that the question mark at the end of this question, the end of the sentence goes, what is it up? So it gets some of that already, but I'm just wondering if you're wanting to control it. If I'm wanting to write the movie script that it's going to, play, I want to be able to tell it, act this scene dramatically or act the scene gently.
Right. Yeah. So the idea would be, I think that some other tool would build on top of this is kind of how I see that kind of working.
Yeah.
By the
Okay.
way, you're making me think, I don't know if the younger people will understand this, but do you remember, what was it, 15, 20 years ago? There was one guy that did the voiceovers for virtually every Hollywood movie trailer.
Oh yeah, Mr. Movie, right? Or whatever. Isn't that
Yeah.
what they called him, Mr. Movie or
And
something like that?
and his
Coming
thing was,
soon.
he did so many of them that his professional goal was, it only took him one take to do each movie trailer voiceover. Otherwise, he didn't have enough time in the day for all the business he got.
Wow.
And so basically, they would have to, what you're talking about, Roger, they would have to tell him, like, this voiceover should be hopeful, slightly lighthearted, but not glib, and it should, and then he would be like, in a world where blah 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 blah, and then they're like, this is like sci-fi, really scary, and then in a world where, and he would do it in one take every single freaking time. But I was thinking, God, if you actually had a database of those descriptors and his voiceover, like to be able to train on that would be awesome.
Yeah, well, then you need kind of this, you need some sort of knob to say, okay, describe that voice, right? Some sort of tagging type mechanism or something like
No, but that's
that.
what I'm saying. If you had the sentence that they gave him to say, how should you read
Oh, I see what
this
you're saying.
voiceover, if you had a database of those plus his
Come up with an
actual
embedding.
trailer.
Yeah,
The
okay.
Mr. Movie embedding.
Yeah, Mr. Movie.
Yeah. Because clearly he had, the ability to translate that into exactly what people wanted.
Yeah. Well, it's a hell of a way to make a living, isn't it?
It may
He had a
exist.
complete monopoly.
Yeah. Well, I've always thought that. I watch home shows. I don't know if you guys watch home shows, but there's these on HGTV. They have these home shows, and they have this one lady, Andromeda Drucker, I think is her name. Her name stuck in her. Her parents are like PhD physicists, so astrophysicists. So there's the Andromeda part. But she, every one of the HGTV shows, like the home shows, she does the voiceover. If you listen, like the House Hunter ones, when they're going to look for a house, she does all the voiceovers, so and so and so and so, we're looking for this, and da, 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 da. So she could use something like this, because I doubt, her voice probably gives out on some days, or she's just not having a good day, and she probably has to do 20 takes, to get it right. So she could do this and just type it in. Anyway, so, like, let's just conclude this here. As we saw and we heard, it actually, does work very well and does produce a very high quality. This is, just beginning. No doubt it will get better. And no doubt people will start building tools on this. I'm actually trying to convince the undergraduate student that I'm mentoring in this particular area that maybe we should look at this. And he kind of blew it off. And I think we're having a call tomorrow. I'm going to try to drag him back. Anyway. So just a few things. It says, despite significant progress, Vall-E still suffers with issues. We observed that some words are unclear, missed, or duplicated in speech synthesis. Okay, and they kind of go into that. And they say, even with 60,000 hours of training, data of training, we can't cover everyone's voice, especially accented speakers. And that's why they got the worst results on that VCTK, which I said was English, but it was from there were a number of non-English speakers speaking English. So it's, probably a little bit more difficult. One thing they mentioned too is since Vall-E may carry potential risks such as spoofing voice and impersonating the specific speaker. There are systems that you've probably seen them in the movies that use, voice recognition as part of their coding sequence. Obviously, this could defeat that. Or if, deep fakes, not just video, but voice, this could be used for that. My understanding is, that they are using older systems. For example, in the new Star Wars movie, James Earl Jones can no longer speak in the voice of Darth Vader. So they're actually using a voice text to voice system specifically for him to do in the new Star Wars movies. So anyway, take that for what it's worth. And they, interestingly, to mitigate such risks, it's possible to build a detection model to discriminate whether the audio clip was produced by Vall-E, and we'll also put Microsoft AI principles into practice when developing further models. I don't know exactly what that means, but I guess that's the, we're going to do something so don't sue us type tag. Okay. So that's all
No,
I
it's
got
the
on this.
pay us even more money so we can like watermark stuff or whatever so that you're protected.
Oh, I see. So we'll give you the Microsoft stamp of approval then that it's genuine or something like that. Okay.
This
Any-
was really cool, Jerry. For your outro, can you like maybe pick a couple audio clips from their website and just play us
Absolutely.
again? I think
Yes.
was there one section where they said variety, like you can give it the same 3-second thing
Yes.
and just
So
generate more than once and get different versions of the exact same thing.
yeah, so here's what they do. All they do is they change in the generators, the random number generators, they change out the seeds. And they can get pretty bizarrely different. So here's the text, because we do not need it. Speaker's prompt.
We live by the rule of law, because we do not need it.
A, B.
Because we do not need it.
So there it changed something. Let's see.
If that's the case, he will struggle. He has not been named. He has not been named.
So you see there was like pauses in there. Let's see, let's try this one.
It's all changed at Kilmarnock.
I think these guys must be in Ireland or something like that.
I must do something about it. I must do something about it.
So there was kind of a different one too. And then here they go into acoustic management here. So you can read the words.
We have Japanese fighting fish.
So that sounds like somebody on a very low fidelity, low voice rate 1960s telephone, right? So
we have to pay obviously a security fee just in case she would damage something, but we have to pay hazardous security fee just in case she would damage something, but
okay. So this was on the old TTS.
we have to pay obviously a security fee just in case she would damage something, but we have to pay hazardous security fee just in case she would damage something, but
okay. Let's do this here. Oh, here.
Her face was against his breast. We have to reduce the number of plastic bags.
Straight down until the end. We have to reduce the number of plastic bags.
That's what Carnegie did. We have to reduce the number of plastic bags.
Let's see here.
Matt, she said, we have to reduce the number of plastic bags.
I've never done these, so let's hear. Just do a couple of
The
these.
lodge in which Uncas was confined was in the very center of the... Notwithstanding the high resolution of Hawkeye, he fully comprehended all the difficulties and danger he was about to incur.
That's interesting here. He must have
That
said
last one sounded really good to me.
Yeah, and did you notice the pause he did between here and there?
Yeah,
So-
like
yeah.
like just freaking pausing when you see a comma, which I think they could build into other systems, I think would help a lot.
Yeah. So, but it was interesting because is
The
there a
lodge
pause
in
here?
which Uncas was confined was in the very center of the...
Yeah, that was interesting that particular thing didn't have a comma in it, his enrollment speech. Let's see here.
As an evidence of wealth is to be classed as a derivative. The ideas also remain, but they have become types in nature, forms of men, animals, birds, fishes.
Yeah, so let's just do this one.
By the way, that last one, there was no comma before but it figured out that there kind of should have been a comma before the word but, and it paused there anyway.
Was it this one? I don't remember which one.
That seems like an advantage here is that it's able, since it's a language model, it gets a larger context, doesn't it? It can infer some of the...
Yeah. One down, the ideas also remain. It paused after remain, even though there's no comma there.
Where are we? One down? Oh, no.
Now two down from where you are.
Here?
Yeah.
Oh, let's do this. Okay, so here's the enrollment voice.
As an evidence of wealth is to be classed as a derivative. The ideas also remain, but they have become types in nature, forms of men, animals, birds, fishes.
Yeah, you're absolutely right.
Try the top and the bottom one, see if it also pauses there.
Okay.
The ideas also remain, but they have become types in nature, forms of men, animals, birds, fishes.
That's really interesting. I wonder if it's learned that, before the word but, there should be a pause, with the language model, that because it's so large, it's learned that. So.
The ideas also remain, but they have become types in nature, forms of men, animals, birds, fishes.
Can you play that one again?
Almost
I think
hear them like breathing.
He aspirated.
That's what I was gonna say.
Yeah,
I think I heard her take a breath before.
Really? Let's try it again.
The ideas also remain, but they have become types in nature, forms of men, animals, birds, fishes.
Let's hear the sample. Maybe the person is just breathy.
Son of my heart, that this fainting lady is your
What?
No. Not
But
3
even
seconds.
if she is breathy, it put
No,
the
she
breath in
is.
the
Do
right
that again.
place.
Okay.
Son of my heart, that this fainting lady is your
After heart, she took a breath. Yeah.
Yeah. Wow.
Wow, that is wild, isn't it?
That's awesome.
Yeah. I mean, from generating this stuff, that is really weird. Let's do maybe one more here, and we'll call it.
And during all that time, he was visited daily. He summoned half a dozen citizens to join his posse, who followed, obeyed, and assisted him.
He put in like 2 commas at least, right?
Yeah.
Yeah. Okay.
It's not necessarily always going to do it right. Like the ones where they emphasize different words, like you might not want that, but it is much more human sounding, far less robotic when you do that.
Yeah. And this is, this paper is what, a couple of months old or something like that. So it's a fairly new system. No doubt they'll get better with it. So, my takeaway is I'm glad I have some Microsoft stock. Maybe I shouldn't have those shares with Google or things like that. But anyway, questions, comments?
Except at that point, I just posted a link. There's somebody's recreated the Vall-E, a PyTorch implementation, I believe it is.
Yeah, I saw that.
I don't see the weight, so I don't know that it's a trained model. They kind of talk about training procedure and everything in there, but a lot of these things, they may come out with something like this, and then you'll get something, like the stability AI, where it's recreated and then the weights are made available to everybody.
Yeah.
It's actually another whole interesting area, I think, to explore for us is that with GPT, there's a lot of models of GPT that are out there.
I'm gonna go ahead and yeah, I'm gonna go stop my screen sharing now, if that's okay with everybody. And we can just